Hidden beneath the hood of every car is a block of highly toxic material, yet it is the most recycled product on the planet, with a recovery rate of up to 99%, far surpassing aluminum cans, paper, and even plastic bottles. This entire transformation begins with solid lead ingots weighing dozens of pounds, moving through a series of heavily automated industrial machines and intense electrochemical reactions before becoming a powerful energy source that starts your engine every morning. In today's video, the Factorin takes you inside a massive battery manufacturing facility to explore how this essential source of energy is created for everyday life. Invented in 1859 by French physicist Gaston Planté, the lead-acid battery holds the record as the oldest rechargeable battery on the planet. Despite more than a century and a half of technological advancement, its core principle has remained unchanged and continues to dominate a massive industry valued at over $70 billion. Each year, more than 500 million batteries are produced, consuming nearly 10 million tons of lead to support over 1.3 billion vehicles worldwide. What is remarkable, however, is that almost all of this lead is recycled and returned to the production cycle, making the lead-acid battery one of the most efficient closed-loop products ever created. The manufacturing process begins with heavy-duty mechanical power as massive ingots of pure lead, weighing up to thousands of pounds, are conveyed directly into a furnace maintained at approximately 896 degrees Fahrenheit. Once the metal is fully melted, the molten lead is immediately directed through a continuous casting system and rapidly cooled with water. Instead of solidifying into large blocks, the system stretches the molten stream into thin strips, which are then tightly wound into large coils, similar to industrial steel rolls. The lead coils are then automatically fed into a ball mill. Inside a sealed chamber, numerous steel balls rotate at high speed, repeatedly striking and crushing the lead strips into extremely fine particles. At the same time, a controlled flow of oxygen is introduced to initiate a chemical reaction, converting the metal into lead oxide powder. Because this material is highly toxic in particulate form, the entire system operates in a closed environment, and workers must use specialized respiratory protection to ensure safety. In parallel with the powder production line, a massive coil of lead-calcium alloy strip is fed directly into the plate grid manufacturing system. In traditional casting operations, molten lead is poured into steel molds, rapidly cooled, and released as formed grid plates within seconds. However, the true efficiency lies in modern expanded metal lines. Here, high-speed steel gear systems continuously punch microscopic slits into the flat metal strip. Almost instantly, a powerful mechanical force stretches the lead outward, expanding and forming it into a uniform diamond-shaped mesh, similar to a metallic accordion. This process produces lightweight grid structures with excellent resistance to chemical corrosion. To complete a standard battery, the factory requires approximately 90 to 100 grid plates. Along the conveyor, laser-based inspection systems scan every fraction of an inch of the surface, immediately detecting and removing any defects before the components move to the next stage. The lead oxide powder is fed directly into a high-capacity mixing system. Inside, steel paddles rotate continuously, blending the material with purified water and diluted sulfuric acid to form a dense, adhesive, dark gray paste. Additives are introduced in precise proportions. Ultrafine fibers improve mechanical bonding and prevent cracking, while an expander maintains a porous structure in the negative plate, ensuring stable performance through repeated charge and discharge cycles. The dense lead paste leaving the mixing system is immediately fed into a high-speed automated coating machine. Metal grid frames move continuously along the conveyor, entering a high-pressure roller assembly. Here, the paste is forced deep into each grid opening, spreading evenly across both sides and filling every microscopic void within the metal structure. The applied pressure is carefully controlled to ensure strong adhesion without distorting the grid. Immediately afterward, an automated scraping system lowers into position, leveling the surface and removing excess material to maintain a consistent thickness across the entire strip. While the paste is still wet and soft, the continuous strip is transferred into an automated cutting system. Precision blades operate in synchronized cycles, dividing the long strip into individual plates with uniform dimensions, ensuring each component meets exact specifications before further processing. The newly formed plates continue moving along the conveyor and enter a flash drying oven. A combination of hot air and flame sweeps across the surface in a matter of seconds, drying the outer layer while retaining sufficient internal moisture to prevent cracking. At this stage, the raw plates are fully formed, with the active material firmly bonded to the metal grid, ready for the next stage of assembly. Although the surface appears dry, the core of each plate remains extremely fragile. The plates are immediately transported by forklifts into curing chambers, where temperature and humidity are tightly controlled. Over a period of 24 to 48 hours, chemical reactions take place as crystals form and bond the active material firmly to the metal grid. This process gives the plates the necessary structural strength and prevents the material from breaking apart under high electrical load. Once they leave the curing chamber, the plates have become rigid and stable, ready to move on to the next stage of assembly. The plates leaving the curing chamber, now hardened and structurally stable, are transferred directly into an automated assembly system. Robotic arms operate continuously, picking up each plate and stacking them in a precise alternating sequence of positive and negative electrodes, forming a fixed layered structure. Between each layer, a separator made of porous polyethylene, PE, or absorbent glass mat, AGM, is inserted. This material allows ions to move freely through the electrolyte while preventing direct contact between the plates, avoiding short circuits. Once the required number of layers is assembled, the entire stack is compressed to secure its position. The process is almost fully automated, ensuring consistent accuracy and high production speed. The solid plate groups, now fully prepared, are transferred directly to the casing station, where the entire operation is carried out at high speed under strict control. Industrial robotic arms pick up each heavy plate assembly and move along pre-programmed paths, stopping precisely above the black polypropylene PP battery case. This material is specifically engineered for high resistance to both heat and acid, ensuring the battery can operate reliably in a chemically aggressive environment. Every robotic movement is fully synchronized with the conveyor system, allowing precise positioning without the need for manual intervention. As soon as the plate groups are correctly aligned, the hydraulic press is activated. Applying substantial force, the system drives each assembly deep into the case, fitting them into individually designed compartments. In a standard 12-volt battery, 6 plate groups are inserted into 6 separate chambers, forming 6 electrochemical cells operating together within a single unit. This pressing force not only enables rapid assembly, but also ensures that the plates remain firmly fixed, preventing any movement under continuous vibration during real-world operation. Once the plate groups are fully seated, a high-pressure air system is immediately activated, blasting across the entire surface to remove any remaining lead particles or metal debris. This cleaning step is essential, ensuring that the internal environment remains free of contaminants and properly prepared for the next stages, including electrolyte filling and final sealing. The plate lugs are then transferred into an automated welding system. Instead of relying on manual torch welding, which is time-consuming and prone to error, modern manufacturing uses cast-on strap COS technology. The machine lifts each plate group, inverts it, and immerses the lug ends into a bath of molten lead, maintained at high temperature. Within seconds, the liquid lead surrounds and solidifies, forming a solid metal strap that connects all the plates within each compartment into a single electrical unit. Immediately afterward, the battery moves to a short-circuit inspection station. The system applies a high-voltage pulse through the internal structure to detect any leakage current or insulation failure. Any deviation is identified instantly and rejected directly on the production line, ensuring the entire internal circuit is fully connected and safe. As soon as the entire internal electrical system is fully assembled, the battery case is transferred to a sealing station using heat sealing technology. A polypropylene lid is precisely positioned onto the opening of the case, while a heating plate simultaneously melts the contact surfaces of both components. Once the required temperature is reached, a hydraulic cylinder applies strong downward force, pressing the lid into place. The two molten plastic surfaces fuse together and solidify into a single continuous structure, eliminating any mechanical gaps or potential leakage points. The entire process takes only a few seconds, yet it creates a seal strong enough to contain the electrolyte throughout the entire operational life of the battery. As soon as the battery case has been fully sealed, a casting machine melts lead and forms the two terminals directly on the lid. The molten metal is poured into precision molds and rapidly cools, creating solid terminals that provide stable electrical conductivity. The terminals are then color-coded for identification, with red indicating the positive terminal and green or blue indicating the negative terminal. In some production lines, symbols such as plus and minus are also printed or engraved to ensure clear recognition. This step completes the external connection points of the battery, making it ready for installation and use. With the terminals fully completed, the battery is transferred to a vacuum electrolyte filling station. At this stage, the system removes the remaining air from each compartment, creating a low-pressure environment that allows the liquid to penetrate deeply into the internal structure of the plates. This process eliminates trapped air pockets within the porous material, ensuring that the entire active surface is fully wetted by the electrolyte. Sulfuric acid H2SO4 is then injected using a precision metering system. Both flow rate and volume are tightly controlled to ensure that each cell receives the exact amount of electrolyte required. The concentration is typically maintained at around 1.28 grams per milliliter, providing optimal conditions for the electrochemical reactions that follow. Over the next 20 to 30 minutes, sensors monitor the electrolyte level in each cell, ensuring that none are underfilled or overfilled before moving on to the initial charging stage. As soon as the electrolyte has been fully filled, thousands of batteries are connected simultaneously to an IGBT-controlled charging system. Direct current begins to flow through each cell, initiating the formation process, which continues for several hours. Under the intense effect of the direct current, the electrolyte begins to bubble vigorously, driving powerful electrochemical reactions inside each compartment. The transformation begins. The inert lead oxide at the positive plate is converted into dark brown lead dioxide, PbO2, while the paste at the negative plate is transformed into porous metallic lead, Pb, with a gray-silver appearance. Because the reaction releases a large amount of heat, the batteries are submerged in a circulating water bath to maintain temperature and prevent deformation of the plastic casing. After many hours of continuous charging and discharging under precise computer control, what was once an inactive mass of material is converted into a fully functional energy source. Before leaving the production line and reaching the end user, every battery must pass a highly rigorous 100% X-Works inspection. An automated measurement system checks the open circuit voltage and evaluates charge retention under light load conditions. Real operating conditions are simulated by applying current for a short duration, allowing the system to assess the electrochemical response within each individual cell. Only units that maintain stable voltage levels and show no deviation are allowed to proceed. Batteries that meet the requirements are then sent through a washing system to completely remove any residual acid from the exterior surface, followed by high-speed compressed air drying. The next stage uses laser engraving technology to apply a QR code directly onto the casing, enabling full traceability and quality control throughout the entire service life of the product. The completed batteries are transferred to the packaging area, where each unit is placed into a dedicated protective box designed to prevent impact during transportation. The boxes are then arranged in a stable configuration on pallets, ensuring even load distribution for safe handling by industrial forklifts. Each pallet is wrapped with shrink film to secure the load, minimize movement, and protect the products from dust and moisture during storage and transit. Once all safety standards are met, the shipments are released from the factory, ready for distribution to dealerships and service garages worldwide. From raw lead particles to a fully functional power source, each battery is the result of a tightly controlled sequence of processes, where every chemical reaction and mechanical operation must be executed with precision. By the time it leaves the production line, it is no longer just a combination of metal and acid, but a reliable energy system capable of operating through thousands of charge and discharge cycles. Follow the Factorin to explore how complex energy systems and industrial machines are built behind industries you rarely get to see.